Hi, how's it going? In this video, I'm going to make a shader. We're going to make our first shader, put a triangle up on the screen. We're also going to understand some of the special keywords used in the metal shading language. We're going to have some fun. So let's jump into it. To start with, I guess, what's a shader? We have our program, and it's going to draw to the screen, and that involves a lot of little pixels. Now, the thing with a GPU is not particularly fast. It's sort of okay. It's not great at making decisions. But what it is great at is multi-threading. It's a massively multi-threaded machine. So when I make a triangle, that triangle has 3 corners. But the interior space, once those 3 corners are calculated, the interior space is parallelized over a massive number of cores, and a whole lot of pixels are drawn at once. Now, I'm sure you're familiar with this, but there are roughly 2 stages to a traditional graphics pipeline. First up, we have a vertex shader, which works on a per corner basis. And then in addition to that, we have a fragment shader, which is going to work on a per pixel basis. So with that in mind, I think that's probably enough info for now. I'm just going to reorganize this project a little bit. I'm going to go ahead and just make a new group, which I'll call for some reason it wasn't displaying the S. That's okay. And then I'll just click New File, and I will make a metal file. Now, the thing is, really, we can write shader source code in any file format we want. We can write it in .text, .h, whatever. But the reason I'm going to write it in a .metal file is so that I get syntax highlighting working. So I'm just going to call this triangle, I guess. We're literally going to hard code a lot of this into the file itself. So what I'm going to do is I'm going to make my vertex function. So the way I make a vertex function is, first of all, I have the name. You can literally call this whatever you want. And I'm going to take in currently just the vertex ID. So it's an unsigned int. Again, I can call this whatever I want. And now I'm going to qualify this parameter with this vertex ID little marker here. And what that does is it signals to the Metal API to fill this parameter in with the vertex ID variable. So just to get a feel for that, I'm going to head over to, this is the Metal language specification. And which page is it? I think it's page 99. I have this prepared ahead of time. So there's this table. These are all of the variable names that we can take in, the inbuilt variables. Amplification count, I'm not doing vertex amplification. That's where you draw one corner, but it actually emits a whole bunch of corners, not just one. I'm not going to do that. Instance rendering, I will at some point, not at the moment, but we have base instance if we want to look at instance rendering. And then we also have instance ID, base vertex, vertex ID. These are some attributes we can use, some inbuilt variables. Now, you'll see that right now this vertex function is complaining. And the reason for that is, of course, every function needs a return type. Now, in, I guess, GLSL, we would mark those return types with the layout qualifiers. We'd have like layout in, and then all the attributes we're taking in. But what we're going to do here is, the standard practice is to actually just return a struct. So I'm going to make a struct, which I'm going to call vertex payload. And the fields of this struct, I'm going to basically describe all the bits of data that I want to be output from my vertex shader and taken into my fragment shader. So we have position, and this is the position on the screen, and this is a special inbuilt variable, so I'm going to qualify this attribute with the position signifier, and we can look this up. If we go to page 68, we have here these mesh vertex attributes. So these are special inbuilt variables. When I set these are not necessarily taken in by the fragment shader, they are intercepted and read by the input assembly, the rasterizer, the intermediate stages between the vertex and fragment shader. So in this case, I'm just using position to set the position on the screen. We have other options like point size. Won't worry too much about that. So in this case, we've just got position, and I'm also going to pass through a color. Now I'm going to do something very exciting, and that is I'm going to use the half precision floating point variable. Now ultimately, when we're working with these things, the fragment shader takes in standard floats and it can convert them to half precision floats. And then when it comes to output things, it does convert them back. When we write to the screen or something like that, write to a buffer or something, it does convert that to a float. But as an intermediate stage, we're using half precision, 16 bits instead of 32, and that greatly increases the speed of any math operations. So you'll see as I go through this, I'll be using half precision more and more in my shaders. It just speeds things up. So what I'm going to do is I'm going to say, hey, this vertex shader is going to output a vertex payload, and I'm almost done. But there's one more really important thing that I need to do, and that is to signify that this shader here is associated with the vertex stage. And the way I can do that is just with the keyword vertex. And we can check this again. Here we are, page 84, right at the top here, functions. We have vertex functions we can qualify. Fragment functions and kernel functions are the major ones. These other modifiers are different, but these three ones are the ones that I usually use. So vertex and fragment, we know what those are. Kernel is associated with compute shaders. So if you have a function that you want to be used in a compute shader, that is signified with a kernel. All right, so in terms of this stuff, I need to return this, of course. So I'll have my vertex payload. I'll call that payload. Return the payload. And then on the other end, I'm going to write my fragment shader. And the fragment shader is going to take in the vertex payload, which I'm simply going to call frag, in this case short for fragment, and I need to qualify that this is an input variable. So under the hood, the vertex shader is run, its payload output is sent to the rasterizer, which interpolates all of the attributes. And then when the fragment shader is invoked, this interpolated payload, I don't know why I'm having trouble saying that, is sent to the input parameter. So what I need to do is simply return the payload's color. I'm just going to convert that to an RGBA. Just like that. So we are all good. All we need to do now is set the appropriate color and position, and this will be based around some data, which I'm going to hard code at this point. To make this triangle, it probably helps to talk about Metal's coordinate system. Let's say I want to make a point, and I want that point to be the bottom left of the screen. The way the x-axis works is negative is on the left, 0 is the center, positive is on the right, and it's normalized between -1 and 1. So to be somewhere on the left, I'm just going to go negative 0.75 down on the left, and then for the y coordinates, negative is the bottom of the screen, positive is the top of the screen. So I'll be down on the bottom, negative 0.75, and for z, positive z is forwards, negative z is back towards me, out of the screen, and this follows the left-hand rule. OpenGL follows the right-hand rule, Metal follows the left-hand rule. So if I take my left hand, and this is a little awkward, but I curl my fingers from the positive x direction to the positive y direction, the thumb of my left hand is pointing into the screen, which indicates positive depth is going to go into the screen. But it really doesn't matter because I want this to be flush at screen level, not behind me, not in front of me. Anyway, and then for the W component, we always hard code 1. I'll talk about that at a later point when we cover transformations, but for now, we'll just go with that. Okay, now for this next point, I want this point to be on the bottom right. So the y-axis does not have to change. The x-coordinate is going to be positive. That's to the right. And then finally, I'll put this next point in the center at the top. So I'll put in 0, neither left nor right, and then positive 0.75 for the y. Excellent. Now I'm going to declare my colors. So I'll just go with the standard red, green, blue. So just note here, we're going to have red on the bottom left, green on the bottom right, and blue on the top center, the center top. So just remember that, because when we get this triangle working, I want to debug this and check that it's working properly. Okay, so let's go ahead and use that hard-coded data to fetch the appropriate position and color for the vertex. I'll say, alrighty, my payload's position is going to be based on the positions array that I declared above at the current vertex ID. And I'll do the same thing for the color. Excellent. So that will work in theory. Nice file. We've written that up. How would we invoke this? So if we go to the renderer, so I've got this render command encoder. I'm going to encode a draw command. Yeah, draw primitives. And then we're going to have a few things. We're going to have the primitive type. And for that, I'm going to go, well, it actually doesn't matter, right? Oh, no, it does. It definitely does. So this is for the shape assembly stage. What this is indicating is for every, what I got my mouse over here, this triangle type, is for every 3 points that I draw, I want the shape assembler to fill in the interior of those 3 points. So I definitely want to go with that. And then we have this vertex start, vertex count, and I think we can actually just remove that and it'll work fine. So vertex start and vertex count, and then to make matters stranger, we have this next step unsigned integer. So let me just go next step, unsigned integer. So my first vertex, I want to start at vertex 0. And then I'm going to be emitting 3 vertices. So hopefully that all makes sense. What this draw command will be doing, currently there is no data bound in any buffers, but this will invoke the shader, start it with a vertex ID of 0, keep incrementing it so it goes 0, 1, 2, we'll be fetching the appropriate positions and colors, the triangle will be visible. Okay, I hope I made that resoundingly clear, but this won't work because we haven't loaded this thing into anything. It's just a file on our disk. So what I'm going to do is I'm going to go through that process. First up, I'm going to import a few things. There we have it. The reason I have these is just, well, IO stream, I'm going to just print a few things out to the console, check that it's working. File stream and string stream are going to be used for basically reading files. I'm going to go to my header. We can leave this now. I'm done with this. I'm going to go to my header and declare a function. There we go. Build pipeline. So I'll just go to my, I know I'm jumping around a little bit. So fair warning, there is going to be a fair bit of typing at this point. This is where the fun ends and the typing begins. So I guess stretch your wrists. So there we go. That was a bit of typing. There's a lot more. But looking through here, the first thing I'm going to do is just print something out. Just want to check that my printing is working first up. I know that sounds weird, but then I'm going to, this should be an input file stream. Okay, I'm going to make an input file stream, use it to open the shader file that I just wrote. Then I'm going to read that all in one go into this string stream. Then I'm going to construct a standard string from that string stream. I love this, so much fun. And then I'm simply going to put that out to the console. So if this is working correctly and I'm seeing my file, then I should see the line reading file and then all the contents of my file. And you can probably tell from that setup that that's not what we're going to see. But let's have a look. So I've got, oh yeah, totally fine. This is just complaining right now that I jumped the gun. Because in the render, although this is good and correct, this will not work until the shaders have been loaded in properly. There we go. So we've got our screen, all good, no errors. But here we just see reading file. We don't see the contents that we expect. Now this comes down to the way Xcode has set the working directory for this project. The way we can fix that is we can just go up the top to the bar. Sorry, you may not be able to see that, but I'm just going to click Product on the Xcode bar, Product. And then down here, we have Scheme, and then I'm going to click Edit Scheme. So a scheme is sort of a launch configuration, you could say. Then I have Options, and right down here, we have Working Directory. So I'm going to go ahead and use a custom working directory, and I'll click on there, that folder, to just set it. I'm going to set it to, let's go with that. Just the file above, folder above, so I can jump into shaders and look at that file. Okay, so now I can try this again, and we can see, we see the line, reading file, and then it's dumped out the contents of our file. That is excellent. So now I'm just going to go ahead and remove those printing lines because they did their job. And now this next part is going to be a little funky, a little strange, but right now I've got all of my source code in a standard string. It needs to be in a next step string. I know, that's just how it is, so that the device library creation function can read it properly. So what I'm going to do is I'm going to declare a new variable, which will be a next step, a pointer to a next step string that will be called source code, and I'm going to do the following. So I guess the big difference here is that, of course, we need a C style string. All good, that's fine. But we also need to specify the encoding format. It's sort of a long one, but there we go. So the next thing is I'm going to go ahead and make a library. Now a library, a metal library, is a object which constructs functions from source code. That's it. It takes in source code, it reads it, it constructs function objects from that. There we have it. Got there in the end. The reason I'm naming these options up above is just to make the code a little more readable. We basically construct that library, run a check to see if that was successful. If it wasn't successful, we print out whatever the error was. Just run this and no error. So as far as I can tell, that probably was successful. Remember I said that the functions can be called whatever we want. They do need to be properly qualified, but they can be called whatever we want. At this stage, I'm going to specify the names of the functions and use the library to fetch them from the source code that I loaded in. It's probably worth pointing out that all of these objects that I've been creating, remember, I'm not using automatic memory management. I'm going to have to manually free them as well. So I'll just go off in the order that I created them. So we made a metal library up above. So down the bottom, I'll go ahead and release that. And then I made these metal functions. But there we have it. So as you can see, I specify what the name of those functions are, and then I go ahead and fetch them from the library. So now the goal will be to basically make a pipeline which uses these functions. In order to make a pipeline, I'm going to make a render pipeline descriptor. A lot of objects, we first make a descriptor for them, and then we create them. There's two major points to this. One is it's a great idea. If we're going with high performance, then we want a low amount of error checking, preferably none. And so it's a great idea to declare as much state as possible up front, which is what a descriptor does. And then if we want to, at a future point, make more objects, then having that state already described. Like descriptors can be reused to make objects. They can be reused with minor variations to make slightly different objects. So let's make a render descriptor. Okay, so here we've got, here we've gone ahead and created or allocated a new descriptor. We've set the functions, and then I'm going to need to set the pixel format of the color attachment that we're rendering to, and this syntax is going to be a little verbose, but bear with me for a second. So I'm going to get the descriptor, and I'm going to access its color attachments. You can check, just jump to definition, control click, jump to definition. And we see that this returns a metal render pipeline color attachment descriptor array, pointed to one of those. What a nightmare. That's okay. Here's how we deal with that. I'm going to go object, and see we have this object, and then we take in an index. This is basically sort of like accessing an array. Going to get the 0th color attachment, and then on that color attachment we are going to set the pixel format. And we can check the pixel format by going, I want to say, to the view delegate, maybe the app delegate. There we go. Here we go, and we have the pixel format we're setting here is whatever this is. I'll grab that. I mean, in principle, this shouldn't be too hard, because if I run this with the wrong value, it will throw an error and say, hey, this is what you should be using instead. So a bit of a nightmare, but there we go. We have successfully set the pixel format that we're expecting. Now, the next thing I'm going to do is I'm going to use this pipeline descriptor to create a pipeline, or as it's called in Metal, a render pipeline state. So in order to do that, this is an object that I'm going to need to save. So I'll go to the header and say, all right, in addition to all this, I'm also going to have a Metal, render pipeline state, which I'm just going to call triangle pipeline. That's nice. So I'll go back and create that. and then down below, I will do an error check for it. So again, this is basically describing the pipeline. We can then use that object to actually make one. Of course, we are going to need to free the descriptor. And it probably is a good idea just to run this right now and check that it works. Build succeeded. Excellent. We're finally back to where we were earlier in the video. So yeah, we do want to draw, but before we draw, we want to get the encoder and say, hey, encoder, set the render pipeline state to my triangle pipeline. There we go. How nice is that? How simple is that? We say, all right, we're going to use that shader, which we've all got that set up, and then we just run it. Let's test it. Nice. Okay, so I just want to verify that the triangle is working. We have the bottom left is red, the bottom right is green, and the center top is blue. Now, furthermore, I just want to highlight how cool Xcode's GPU debugger is. So as this is running, we have some options down here, specifically this M. So if I click on this M logo, I can capture a frame. There we go. And I mean, we can play around with it. So we can see in the overview, yep, we have one command buffer, one render encoder, one draw call. Very, very simple. It's taken 44 microseconds or something to execute that. I can click over to my dependencies to see how the operations depend on each other. So I have my render commands, they do their thing, and then the present is executed after the render commands. Okay, great. On the left here, I can click over to performance to see various metrics. So we have bandwidth is changing and things. Let's have a look at occupancy, I guess. We can see the three major types of shaders: vertex shader, fragment shader, and kernel or compute shader. So we can see, for instance, if I go up here, my vertex occupancy is basically 0. I'm doing very little vertex-wise. Fragment-wise, get to about 14%, 13%, 14%, and that makes sense because the fragment shader is, although it's very simple, it is being invoked over a large area. So it sort of makes sense to me, at least. Anyway, that was all I really wanted to look at the moment. Got our shader there. That's nice. I'm having fun. Look, I hope that you enjoyed this session. Hope things are going well for you. And yeah, have a good one. Bye.